Welcome to the second lecture of week 2, and here we are discussing design of heads. This topic we have started from the previous lecture where we have discussed different types of heads, and in this particular lecture we will discuss procedure to design these heads. So, as flat head is the simplest one, we will start design from that and then we will proceed towards conical head and then for dished heads. Okay. So, let us start with design of flat heads. Now, in this case we will calculate thickness of flat unstayed circular heads and covers. Okay. So, you see here we have one term, that is unstayed circular heads. What is the meaning of unstayed circular head? To illustrate this or to make you understand, I am taking the example of this glass. Okay. Now, if you see this glass, this is open part of this glass where I need to cover. So, what is the meaning of unstayed? To understand this, let us first discuss what is stayed. So, stayed means when we have when this is the opening which I need to cover. So, what I do, I put some of the metal strip and that those strip will be welded at its edges. For example, I am taking one strip of this much diameter, I hope you are getting this, one strip of this much diameter, one section will be welded over here, another would be welded over here. Similarly, another strip of same diameter and another strip of same diameter. In this way, I will put different strips and over this the head will be stayed. So, it is basically gives more strong positioning of head. Okay. But here we are discussing unstayed where this type of structure or this type of support is not available to the head. Even that type of structure can be used in the shell also to make to keep its geometry regular. For example, if I am having this glass and this is the whole length of the shell. So, that type of structure, it means when we weld the strip at two edges, when we keep the length of those strips equal to the diameter of the shell. So, it means when we weld it, it will keep its shape circular only. Okay. I hope you are getting it. So, that is that type of structure usually used in pressure vessel when it is having larger diameter, but it does not interrupt the process because in between it has very open space for fluid to move. Okay. So, here as far as design is concerned for flat head, we are considering design of unstayed flat heads. So, to calculate the thickness of flat head, we can use the following expression. As you see, this is the expression which we will use. Here T is the minimum thickness of flat head and that is equal to CD by 10 root over P by F, where P is the design pressure in kg force per centimeter square and F is the allowable stress in kg force per mm square, and due to this here we have the term 10. If I am considering pressure and allowable stress in same unit, that is Newton per meter square, then this 10 will not appear. In this formula, T, which is the minimum thickness, is found in mm and C is the factor that depends upon the method of attachment to the shell. It means how this head is attached to the shell, accordingly value of C varies. Okay. And further, D is the diameter or short span measured. It means D is not always the diameter. You can consider this as an effective diameter which will depend on how head is attached to the shell. Okay. And here I am having this expression where T equal to CDE root over P by F, where both pressure and allowable stress values are in Newton per meter square. So, in books you can find this expression. This expression is available in IS 2825 1969 code. Okay. So, here in book instead of D it is DE is mentioned, where it is called as effective diameter. C is the factor Okay. So, depending upon different attachment, now we will see how to find out the value of factor C as well as D, that is the effective diameter. Okay. So, let us start that with the flange flat head butt welded to the vessel. For this connection we will see the value of factor C as well as diameter. Now, if this is the image where if you consider this particular section is resembling to the shell and over the shell head is attached. So, if I consider placement of this, that placement is horizontal. Okay. So, this head is attached to the horizontal shell. Okay. So, Ts is the thickness of standard thickness of shell, and this T is the thickness of flat head which we need to find. And here you see in this particular section, this is basically the curved part or formed section. This is not a flat section, this is flat formed section. Okay. In that case, D will be Di. Di is what? Di basically inner diameter of head. Okay. And C is the factor which has the value 0.45. So, when we have flange flat head butt welded to the vessel, we can consider C and D in this way, and then these value we can put in this expression to calculate the value of thickness. Now, further we have another attachment or another connection. Further we have another connection, and that is plates welded to the inside of the vessel. So, how it looks like? Here I am having this shell, okay, and inside this shell head is attached. If you consider the previous diagram, there head is attached to the shell through butt welding. I hope you remember the different types of welding which we have discussed in lecture 4 of week 1 in weld joint efficiency factor. Okay. So, here we have this flat head which is attached inside to the shell, here also and in this diagram also. Now, what we need to focus on, that if you consider this section, okay, or if you consider this section, why this section is so black? Okay. This section is so black because when we are welding it, okay, when we are welding it, the material through which it is welded like iron, that is filled inside the corner. Okay. So, that is filled inside the corner, and when that filling is higher, we call that as fillet. So, this black spot in this diagram as well as in this diagram, these are nothing but the fillets. It has a particular thickness as 0.7 into Ts. If it more thick, it will be called fillet, otherwise that will be simply looking like a joint. Okay. So, when this type of connection I am having, D should be equal to Di and C value should be greater than 0.55. Now, if you compare this image with the previous one, previous figure has form section. So, there C value was 0.45, but in this particular case form section is not there, flat head is directly attached. So, C will have greater value than 0.45, and if you remember the expression for thickness, thickness is directly proportional to C. So, when C value will be small, T will also be small. So, in formed head we can have less thickness in comparison to flat head as we are discussing now. And next we have is a plate welded to end of the shell. For example, if it is attached like this is the shell, and here we have this attachment of head. So, if head is welded at the end of shell, in that case D would be Di and C would be 0.7. Okay. Now, if you compare this image as well as this image, in this image I am not having any fillet. However, in this case fillet is made, and that fillet will give slight curvature to this sharp corner, and here stress distribution will be more uniform in comparison to this figure, and therefore, C value would be 0.7 over here, but here minimum C value would be 0.55. Though it is mentioned greater than or equal to, so if it can work with 0.55, keep that value equal to 0.55 only. Now next connection I am having is plate welded to the end of the shell with additional fillet weld on inside. Okay. So this is nothing but the previous diagram only. At the end of shell, head is attached with fillet. So you can see the value of C, and D would be DI in this case. Now next I am having is covers riveted or bolted with the full face gasket to shells or flanges. So this connection is looking like this, where if I am having this flange section, okay, flange is basically used to join two parts having same diameter. Okay. In detail, the flange design will be discussed in week 3. Okay. But for a time being, you can understand that it will be used to connect pipe of same diameter. So you here in this diagram you see this is one section of flange, and over this we have flat head. So this is connected to the this flat head is connected to the flange. Now here you see full face gasket. Full face gasket means this whole surface of the flange is covered with gasket. So if I am having circular pipe, this particular section is placed around this pipe, and this section will also be circular. So circular gasket of this much diameter will be kept over here, and therefore it is called full face. Now if I need to attach this flange with flat head, here these two assemblies are connected through bolt. So one bolt is available here, another is available here, and around the periphery different bolts are available, and it gives the diameter that we are showing as D in this diagram, and which is called as bolt circle diameter. Now if this is the case, D would be D as it is shown over here, and C value would be 0.42. Further, if we have covers with a narrow face bolted flange joint, that is gasket is placed within the bolt circle. Now how it will look like? If you see, here it is horizontally placed, and here we have demonstrated with vertically placed head with the flange. Here head is placed with the flange in horizontal manner. Now if you see this particular section, this is basically the gasket which is placed within the bolt circle. Bolt circle is one edge is this, and second edge will be up to here. So that so within that bolt circle this gasket is placed. Okay. So here we have different dimension like D, H, G that you can observe from this figure. So D is basically mean diameter of gasket, and C you can observe from this, which is equal to 0.31 plus 190 FB Hg by PD cube power 1 by 2. So here FB is basically bolt load in kg force, Hg is 0.5, bolt circle diameter minus D. So bolt circle diameter minus D, and half of that will be equal to Hg. So in this way you can find values of C as well as D for different connections, and whatever connection is present in your case, you can compute the thickness of flat head for that case. Okay. So in this way we design the flat heads. Okay. And next heads I am having is the conical heads. Now geometry of a cone may be compared with that of cylinder, in which the diameter is continuously changing. Okay. So conical shape, if I am considering, it is like this. So diameter is continuously changing from top to bottom. This suggests that cylindrical shell equation can also be used in this case, provided the diameter is appropriately modified, incorporating the conical shape of the cylinder. So as this diameter is continuously changing, we usually design conical way in two ways. First is we compute thickness of head at the junction. Now what is junction? Junction is basically the part where it is attached to the shell. For example, if I am having this conical shape, you can see this image where this conical shape is there. You see, this is the conical shape which is attached to the shell. Okay. So, wherever this curved part is there, or wherever if that curved part will not be there, it will be directly attached to the shell. So, at the junction means at this part where it is attached to the shell. For example, if I am having this curved section, then this curved section will be the part of conical head, and somewhere here it will be attached to the shell. So, in that case, at the junction means wherever this curvature occur. Okay. And if that curvature will not be there, it is directly attached to the shell. So, at this point we compute the thickness of conical head at the junction. So, at the junction means this part, whether it is attached to the shell over here or not. Okay. Thickness of this part we will compute as that at the junction. So, one thickness is at the junction, second thickness is away from the junction as diameter is continuously changing. Okay. So, we will compute thickness away from the junction. Away from the junction means to this side. Okay. If I need to calculate the thickness for this section. Okay. So, that will be calculated away from the junction. Away from the junction means L distance away from the junction. So, what is that L, how it will be computed, that all we will discuss. Now, if you see this diagram here, a few more points I need to focus. If you consider this Ri, what is this Ri? That is the radius of knuckle part. If knuckle part is there, because if you remember we have discussed in conical head that if apex angle exceeds 60 degree, it means the conical section should have curved or knuckle part. So, that knuckle part must have the radius Ri. Okay. So, that you can see in this diagram. DE, if you see, D is basically outer diameter of head, and here we have dk. Dk is basically the diameter where I am computing the thickness, and alpha is half of apex angle. Usually this section is defined as the apex angle. So, alpha is half of apex angle, and in this case angle psi is also given. So, for this case psi is equal to alpha. So, why these two terminology are used for same purpose? Because there are some cases where psi is not equal to alpha. To discuss, we will discuss that case also. So, to distinguish the two cases, alpha and psi are two different angle which are used in conical heads. So, as far as design is concerned, first we will start design from the junction. So, we will compute thickness of head at the junction. At the junction you have understood, it means we are computing thickness at this section. So, thickness of cylindrical and conical section within length L from the junction shall be determined as T equal to P d naught C by 200 Fj. This expression we will use, and I guess you understand why this 200, because F and P are in different units. P should be in kg force per centimeter square, and F should be in kg force per mm square. So, this expression is available in code. Where J is the joint efficiency factor, D is the outer diameter of conical section. Okay, D is the outer diameter of conical section, as you can observe, you can find from this image, and C is the factor taking into account stress in the knuckle. So, according to these knuckle, factor C vary. So, according to this knuckle, factor C varies. That we will discuss how it varies, and L is the distance from the junction, which can be found as 0.5 root over dE into T by cos psi. So, this expression is used to calculate L, where this T is basically the actual thickness of head at the junction. And then considering this thickness at the junction, we will compute distance L to calculate thickness L distance away from the junction. I guess you are understanding this. So here you see psi I am having, psi is the difference between angle of slope of two adjoining conical sections, and I have already discussed why this psi is there. Psi and alpha both angles are there, but in some cases these two angles are different, therefore we have used different notation for these two. How it looks different, that we will discuss. And next parameter I am having is Ri. Ri is basically inside radius of transition knuckle, which shall be taken as 0.01 dk in case of conical section without knuckle transition in mm. So if you see this Ri basically denotes the knuckle transition part, and if knuckle transition part is not there, then Ri will be equal to 0.01 dk. Okay. So that value I need to consider while designing. And what is dk? It is the inside diameter of conical section or end at the position under consideration. So wherever I am finding the thickness, diameter at that particular section will be denoted as dk. For example, if I am finding at the junction, dk will be equal to di, inner diameter at that particular section. Now in this slide we will see how to find out value of C as a function of psi, and this is not R1, this is Ri, Ri by dE. Okay, this is table 3.6 in code IS 2825. You can see you can find this table as 3.6. Now if you see this table here, in first column I am having different angles of psi, okay, and here we have Ri by dE, here we have different value of Ri by dE, and all these values you see, all these values are nothing but value of C. So if I am not having different value of psi as well as alpha, I can consider psi equal to alpha. Okay. If it is different, that difference will be mentioned. Okay. Now we have two conditions, that when knuckle part is there and when knuckle part is not there. So when knuckle part is not there, it means Ri would be equal to 0.01 dk, and dk, if I am calculating thickness at the junction, dk should be di. Okay. And if you see this table, here we have Ri by dE, and here dE, if you remember, that is nothing but the outer diameter, and for calculation purpose we can assume di should be equal to do. It means dk should be equal to do. It means Ri by dk should be equal to 0.01. So what is the conclusion? If I am not using knuckle part, it means C value you have to find through this column only, corresponding to different psi value. For example, psi is given as 45, and in the problem it is mentioned that knuckle part is not given. So you can use this table as corresponding to 45 and Ri by d is 0.01, value available as 2.05. So that 2.05 you can consider as value of C. However, if I am having knuckle part, Ri by dk will always be greater than 0.01. So considering the value of Ri by dk, you can understand whether knuckle part is there or knuckle part is not there, and this point will be more clear when we will solve a few examples based on this. And now we have thickness of conical part away from the junction. As we have discussed, away from the junction means L distance away from the junction. So to calculate thickness of that part, we have this expression as T equal to P dk by 200 Fj minus P into 1 by cos alpha. Okay. Here P is the design pressure, Y 200 is there. I hope you have idea about this till now. Because P and F are having different units, J is the joint efficiency factor. So if you see this expression, what is dk? Dk you can see from this diagram that where I am finding out the thickness, inner diameter of that part will be called as dk. Okay. So if you consider this particular section, this section we can use to find out value of dk. okay, as it is shown in this diagram more clearly. So, for example, this is dk and here we have A, B, C and E and F. D I am not taking over here as dk and di are already included alphabet D. So, here we need to find out expression of dk. Okay. Now, if you see, this is basically dk, and to compute dk I have to focus on this part. Okay. Now, further corresponding to this I can draw a line over here and I can focus on this particular section. So, if you consider this section as well as this section, we can apply equal angle theory here. So, here sin alpha, if I need to calculate, sin alpha would be CE by BE. So, sin alpha would be CE by BE, and BE is nothing but length L. And CE, how you can compute? FE minus FC by BE. Using this geometry you can find out. I think that you can make, it is not very much complicated. FE is basically DI by 2 and FC is DK by 2, that you can see from the geometry, and this B is nothing but the L. Then further I can replace DI with this, where this TS is the standard thickness of shell, because it is available at this particular section where conical section has equal inside diameter to shell. And further resolving this expression you can find out the final expression for dk. So, dk you can find out in this way. So, here we have conical section and we have seen design of thickness at the junction and away from the junction. In this slide you can see, if you can focus on this particular image, here we have angle alpha and psi. So, both psi is equal to alpha in this particular figure. However, if I am focusing on this, here we have this alpha 1 and here alpha 2 and psi. So, here basically psi as well as this alpha, these angles are different. So, if conical section is placed in this way, we can have different value of psi and alpha. So, this psi and alpha may be same or may not be same. So, that depends on how conical section is made. Okay. So, that was about the conical section. Now, we will discuss design of torus spherical head as well as ellipsoidal heads. So, these heads are basically coming under dished or formed heads. So, you see this image where this figure is of torus spherical head and this figure is of ellipsoidal heads. So, both heads are basically dished heads. However, in ellipsoidal head we have more curved part in comparison to torus spherical heads, and these two heads are designed using same expression as these are dished heads. So, thickness of the end or thickness of the head for these heads. So, thickness of dished heads can be determined by following expression, which is T is equal to P d naught C by 200 Fj. So, again here I am having 200. So, that I guess you understand, I do not need to repeat that again and again. So, here you see the main point to be considered is how to find C. C is basically the shape factor, and how we can find the factor C, that is the main concern over here. Other parameters how you need to take, that you already aware. So, let us discuss how to find out value of C. Now, if you consider this particular slide, here I am having this image. If you see this, here I am having this image which is figure 3.7 in IS 2825. So, that figure you can refer. Okay. So, y axis of this figure is having factor C, whereas x axis have value of He by d naught. Okay. So, once I will calculate He by d naught, I can find value of C, and if you observe this graph, here I am having solid lines for T by d naught when it is varying from 0.002 to 0.04, and here also I am having broken lines, and these lines again vary from 0.5 to 5, okay, and on this axis we have d by root over t into d naught, okay. So, this image I have to use to compute the value of C. So, first of all, to use this we have to find He by d naught. D naught is the outer diameter of head or shell. So, that we already know. How to find out value of He, that I have to speak on. So, He is basically effective outside height of the end, and that can be determined as, here we have HO dO square by 4 RO and root over dO RO by 2. So, to compute He we need to find H naught, we need to find this expression, we need to find this expression, and whichever is minimum, that I need to take as He value, and whichever is minimum among these three, that I need to take as value of He. Now, why this why we are taking minimum among these three as He? Because when I am having minimum He is basically, if you see the diagram, if you focus on this particular slide, He is basically that this height. He is basically this H naught, that is effective height, okay. So, if I am having more value of He, it means it has more curved part and it will include more manufacturing cost, higher manufacturing cost. Therefore, if I am having three different values to find out He, I will select the minimum one. Now, among these three value, HO you can find out using this expression, where RO, DO by 2 and small ro, all these values you know about the head, and similarly this value I will found and this value I can found, and I will choose the minimum value among these three as He. So, we have seen that how He will be computed, and once He will be known, in this figure you can make a line, okay. When let us say He is 0.2, so corresponding to 0.2 you can make a line, and how you need to find out value of C is, when ends are fully compensated, read C from full curves, that is T by D naught 0.002 to 0.00, that is T by D naught equal to 0.002 to T by D naught 0.04, and we can make interpolation also. So, how you need to compute this? If you see the expression, T is equal to P D naught C by 200 Fj, okay. Now, here you need to find C. So, how I will further consider is T by D naught, because if it is fully compensated, we need to see value of T by D naught. So, T by D naught I will extract, and if you consider this expression, okay, this whole expression will be a constant. So, this whole expression will be a constant, let us say that value is x into C, okay. So, corresponding to He by D naught 0.2, you need to choose value of T by D naught and corresponding value of C in such a way, so that this expression should be satisfied, okay. So, I hope you are getting how to find out value of C, and it will be more clear when we will solve a few example based on that. There I will elaborate this in more detail. Now, when end remain uncompensated, read C from broken line, that is D by root over T into D naught equal to 0.5 to 5, it is varying, as you can see from these broken lines, okay. So, what is this compensation and uncompensation? That we will cover in lecture 4 and 5 of this week. So, basically when we make any opening, that opening may be compensated or may not be compensated. So, based on that we considered design of heads. So, till now you please bear compensation and uncompensation as it is. I will elaborate that when time comes, okay. So, if you consider this statement here, small d is basically diameter of largest uncompensated opening. For example, in head I am preparing 2-3 openings. One is having, let's say, diameter 0.05 meter and another is having, let's say, 0.7 meter. So D would be 0.7 in that case. So considering that D, you need to find out value of C for given HE by D naught value. I hope it is clear. Further, values of C corresponding to HE by D naught you can find from table 4.1a as well as B from book, and this book is a book from B.C. Bhattacharya. So that book you can use. So table 4a, this is basically table 4a which is used for without opening or with fully compensated openings, and here I am having different value of T by D naught which is varying from 0.002 to 0.04 as it is appearing in the graph, and here I am having different value of HE by D naught, and all these values are values of C. Okay, and this table I am having is for uncompensated opening, or that is table 4.1b, where D by root over T into D naught is shown from 0.5 to 5, and corresponding to HE by D naught you can read different value of C from this table. So in this way you can use that graph as well as this table to find out value of C for torus spherical as well as ellipsoidal heads. So as I have discussed that torus spherical head as well as ellipsoidal, both heads are designed using same expression. So what is the difference between these two? Difference will lie when I am having major and minor axis. Okay. So when I am considering ellipsoidal head, it has a specific major and minor axis, and accordingly HE by D naught value will vary. However, that major and minor axis ratio is not maintained in torus spherical head. So based on HE by D naught you can find different value of C for ellipsoidal heads as well as for torus spherical heads. So in that way you can make the different design for these two heads. Now here we will add 6% extra in T for reduction in thickness as torus section. So when I am preparing the forming section, some material is lost. Therefore, we consider additional material while designing that forming section. So if I am considering torus spherical head, ellipsoidal head, conical head with knuckle or flat formed head, wherever I am having that form section, I will add 6% extra to the minimum thickness. That guideline you need to follow. Okay. So once I am having this, we will calculate the blank diameter. What is blank diameter? It is the diameter of plate with which formed ends can be fabricated. Okay. So if I am having this ellipsoidal head, the diameter means the diameter of this whole section, whole plate through which this ellipsoidal head is prepared. So that would be equal to D naught plus D naught by 42 plus 2 by 3 Ri plus 2 SF. SF you can understand, SF is basically this straight part which is beyond the curved section. So for T is less than 25 mm we will use this expression, otherwise we will use this expression. Okay. So based on these we can find out blank diameter, and here I am stopping lecture 2 of week 2. I will continue design of heads in next lecture, where I will illustrate a few example for design of heads, and that's all for now. Thank you.